Don't forget to subscribe and press the bell icon to never miss a video from testbook.com.
Hello guys, very good afternoon. I'm Dhiraj and I welcome you all in the Testbook.com, and I'm here to provide you the best I have. So guys, today I have bring the another revision session for what? For Vizag Steel Management Training, right? Recruitment and for mechanical. So guys, we are going to start. But before that, what you have to do? You have to hit like, share and subscribe the channel, as well as you have to share the link of this video in your social media group so that the maximum people will get benefited of this session, right? So yes, I can see that few people have already joined. So those who have already joined, they have to share the link as well. Okay. And my dear, we are going to start right now. It's 2:59. We are going to start at 3:02 so that the people will get joined till that time, right? So yes, anybody have any questions, they can ask me. Yes, few people are joining now. Yes. So today is a revision session, okay? And tomorrow we'll go for objective type question as well. And don't forget to do hit like, share and subscribe. So it's right now it's 3. So we are going to start at 3:02. So we'll wait for 3 minutes so that the people will get joined, right? And guys, don't forget to subscribe the channel, as well as you have to share the link of this video in your social media group so that the people will get benefited of this session, right? And the people who already joined, and I want to tell you them that is, my dear, we have one flash sale for what? Testbook Pass. In that we are getting just it for ₹299, and you are getting 100 plus courses in that and 12,000 plus tests, right? And I want to tell you that if you are interested in gate mechanical, then my dear, we have a mega price drop in the gate mechanical, and you are getting it just for ₹3,099. You can explore the preview classes of it in the website as well as in the app. And the people, those who want to attempt a quiz like session, right? What, my dear? Quiz like session. Then I want to tell you that for you guys, we have Gate Fest 2021 Gate Reward Quiz. In that there is a chance to win for at least ₹2 lakhs, right? Prizes, right? Means, and along with the prize, my dear, what you will get? You will get a benefit of practice in the actual gate examination, which will be held on month of Feb. Okay. Along with that, if you are interested in SSC JE Mechanical Live Coaching, then I want to tell you that we have already launched this batch on the 15th of November. The classes is going on. You can explore the preview classes or demo classes in the website as well as in the app. And supposed to be we have any query, you can fill the application form on the link. You can find the link of application in the my dear where? In the description. Okay. So description में आपको link मिल जाएगा. So you have to fill the link so that Testbook counselor will get back to you. Very good afternoon. Very good afternoon. So it's 15:02. Now we are going to start. Now we are going to start, my dear. Okay. So can we start, my dear? Can we start? 15:03. Now we are starting. So here we go, my dear. Here we go. So which subject I'm going to cover today? That subject will be, my dear, none other than that is I'm going to cover, that is, my dear, today power plant engineering. What? Power plant engineering cover करेंगे आज. क्या cover करेंगे बच्चा? Power plant engineering. Okay. Very good afternoon, Rahul. So see, now just watch and listen what I'm saying. So before starting power plant, as we start the power plant, that means, my dear, what we'll do? What we'll do? We are going to differentiate between the gas power plant and my dear steam thermal power plant. Okay. So here we go. So my dear, here I write that it was steam thermal power plant. You should know the difference. Steam power plant. And my dear, it is what? Gas. It is gas. Okay. Now listen to me. It works on Rankine. It works on what? Breton. One, that is what? Fuel is what, my dear? Here. Fuel is what? Coal, oil, etc. Right? Here you can use, my dear, what? Natural gas. But you can use natural gas, methane, etc. यहाँ पे gases you are allowed to use. Here you can use, my dear, coal, oil or anything, right? What else? Here, my dear, the highest temperature is what? 620 degrees centigrade. Here 1300. कितना highest temperature जाता है? We have highest temperature of RAC has been over in the morning. Rakhil Gunda. You can see the RAC has been over in morning at 11. Okay, it is 620, it is 1300 degrees centigrade. What is pressure ratio? If I talk about the pressure ratio, my dear, it have the pressure ratio in the range of 182, 300. It have, my dear, 8 to 12. कितना होता है इसका? 8 to 12. Okay. And I want to tell you, it's weight to power ratio. Weight to power ratio इसका कितना है बच्चा? It have 55, and it have the weight to power ratio. That is what, my dear? kg, 20 kg per kilowatt, right? It have 50 kg per kilowatt. Okay. Now, what should be the thermal efficiency? So, iska thermal efficiency is around, my dear, 35%. And it have 20 to 25%. Okay. You got it? Okay. That is 35%, 20 to 25%. Okay. Pollution, it creates the highest pollution. Steam thermal power plant creates a high pollution. When I come to the gas, it have less as compared to that of steam thermal power plant. Okay. Now, my dear, I'll go for next. And here I'll start what? Gas thermal power plant. And in that we are going to see what we have. We have Brayton cycle. We have Brayton cycle, right? And in the Brayton cycle, what we have, my dear? In the Brayton cycle, what we have? In Brayton cycle, there is a first thing. It is what? It have two types of cycle: open cycle and closed cycle, right? You know that. I'm not going to draw the diagram. Okay, diagram draw nahi karunga. Okay, it have two cycle. That is open cycle and closed cycle, right? That is closed cycle have some advantage. So I'll discuss the advantage of closed cycle. Advantage of closed cycle. Right, the first one. First one is what, my dear? More efficiency is high as compared to this one, right? Better working fluid. Better working fluid can be used. Better working fluid can be used. Okay. And what we have seen, my dear, इसमें और क्या देखा था हमने? That is what? It can work below atmospheric pressure. Work below atmospheric pressure. ATM pressure means what? Atmospheric pressure. Okay. And what thing, my dear? No problem of, there is no problem of, my dear, blade erosion. But it has some disadvantage, and that disadvantage are what? It is bulky. Complex design is what? Complex design, and it is costly, and it is not due to bulkiness. It is not able to. It is not able, or we can say we are not able to use it in aircraft refrigeration system. And I want to tell you that what? That is, it is bulky, complex, and costly. Okay. The one thing I want to tell you, because whenever it is going to operate below the atmospheric pressure, so we want to be a very perfect leak proof, right? So leak proofing is difficult. Is difficult. Okay, my dear, wait for a minute. Okay, give me a minute. Though, give me a minute, okay? Okay, that is what leak proofing is difficult. Okay, now we are going next. Next, we are going to see. After that, we have seen what we have seen. We have seen assumptions. Assumptions for what? For what, my dear? For Brayton cycle efficiency. And my dear, in that we have seen air is only working fluid. That is Cp, Cv, and gamma is not function of temperature, right? And we have taken that about there is no heat loss. No heat loss, right? And there is no pressure drop. And we have also seen that is what, my dear? No heat loss, no pressure drop, change in kinetic energy and potential energy is what, my dear? Negligible, or we can say zero. Is what? Zero. Okay? That we have seen. Guys, do hit like, share, and subscribe the channel. And if you are interested for GATE Mechanical, you can fill the form which is mentioned in the chat box. Okay. And my dear, that is what these things we have seen in what? Assumptions. These are the assumptions required for deriving the expression for what? Efficiency. And my dear, when we derive the efficiency for the Brayton cycle, that comes around. Kitna aaya tha bacha? It is none other than 1 upon pressure ratio. It is what? RP. RP is a pressure ratio, and it is what, my dear? Gamma minus 1 upon gamma. Okay. That is what? Yeah, RP is RP, that is what? Pressure ratio. RP is what, my dear? Final pressure divided by initial pressure. Okay. And then we have seen the variation of this efficiency with respect to what, my dear? Pressure ratio and gamma. Right? This is what? Efficiency. This kind of variation we have seen. It is what? Pressure ratio, and it is a value of what? Gamma. Right? Supposed to be gamma is here 1.4. Here we have, my dear, gamma 1.6. So efficiency is what, my dear? Efficiency of Brayton cycle. We have seen that is function of what? RP and gamma. Okay. Here we go. And after this, my dear, while deriving the efficiency, we also come across that is what? T2 is equal to T2, T4 is equal to T1, T3. This formula you have to also keep in mind because it is very helpful for solving the numerical in between. Right? I hope you got it. Here we go. And my dear, after this, what we have seen? We have seen the back work ratio. What, my dear? Back work ratio. It is nothing but what, my dear? Negative work divided by positive work. That is this one. Right? We have seen, my dear, what? RW. That is what? Work ratio. And it is none other than what, my dear? Net work divided by the work produced by turbine. That is what? WT. So it is what? W net means what? WT minus WC divided by WT. And we have seen, my dear, what? RW is equal to 1 minus back work ratio. This you have to keep in mind. ये भी हमने देखा हुआ है. Right? Right now, this is all about work ratio and back work ratio. I hope it's clear to you. Okay. And after this, my dear, what we have gone for? Then we have seen specific fuel consumption. What? Specific fuel consumption. And in that we have seen SFC is equal to, my dear, what? Mass flow rate of fuel divided by what? Power. Okay. And it is in what, my dear? Kg per second. And it is in what, my dear? Kilowatt. Okay. Then, my dear, I want to let you know that we have seen air rate. Air rate, and formula for the air rate is nothing but, my dear, what? 1 upon the, 3600 divided by W net. That is what its unit is what, my dear? Kg per kilowatt hour. Okay. Then we have seen, my dear, specific fuel consumption again, and it is none other than 3600 divided by what, my dear? Air fuel ratio into W net. Okay. And it is again, the unit will be what, my dear? Same as that of air, kg kilowatt hour. Right. Okay. Just watch. And after this, my dear, we have seen, क्या देखा था? इसके बाद we have seen, that is maximum what? Maximum pressure ratio. And we have found out the maximum pressure value of Rp max is equal to, my dear, T max, that is T3. Or I can say directly, right? T max divided by T mean raised to power, my dear, what? Gamma upon 2 into gamma minus 1, right? In the same way, we have also find out. Then, my dear, by applying this, we have find out, as you know, efficiency is function of what? Pressure ratio and gamma. So, as your pressure ratio has been increases, that is Breton efficiency will going to be increased. At Rp max, what we have efficiency? So, eta max of Breton cycle will be, my dear, what? 1 minus T1 by T3. Okay. And it is what? It is equivalent to eta of Carnot. Okay. And my dear, I want to let you know one more thing. That is, you can find, because if you are increasing efficiency continuously, you have find, that is pressure ratio continuously, for sake of getting an increment in what? Efficiency. My dear, you at the same time, you find that the work done has been reducing. So we are interested in optimum pressure ratio, right? So optimum pressure ratio is, my dear, is optimum pressure ratio, Rp opt, that is optimum. It is none other than, my dear, T3 by T1 raised to power what? Gamma upon 2 upon gamma minus 1. Right? Wait. Rp optimum. Let me write. Rp optimum, we find, my dear, this one. That is what? T3 by T1. T3 by T1 raised to power. It is in under root, raised to power 1 by 2 into what, my dear? Gamma upon gamma minus 1. Okay. Sorry, it is not 2. Okay. Here it is not 2. So it is C. You can see. Now can I say this Rp optimum is equal to T3 by T1 gamma upon gamma minus 1 is nothing but Rp max. Rp max raised to power 1 by 2. That is Rp optimum we got, my dear, directly. That is Rp max under root के अंदर, right? I hope you got it this point as well, my dear. Okay. And after this, we have gone for efficiency of combustion chamber, right? Efficiency of combustion chamber. And before that, we have seen the graph of like this. I'll tell you. See, in that, okay, and there is another graph like this. This is Rp. This is also Rp. This is what, my dear? This is efficiency. And this is what? W. This is what? W. So you have find that as you are increasing Rp, you get what, my dear? You get increment in what? Efficiency, right? Continuously. Okay. My dear. But when you are increasing pressure ratio continuously, you will get at Rp opt, you will get maximum value of what, my dear? This pressure ratio will be known as what? Rp optimum. At this pressure, my dear, your efficiency as well as your work is maximum, right? But supposed to be for increasing beyond this, you will get drop in work, right? This thing I have to explain. So I have to explain, my dear. This is graph of, that is pressure ratio versus work and pressure ratio versus efficiency. My dear, we have seen then. We have what we have seen after this. We have seen, that is process to improve what? efficiency, and that is first thing we have seen, regeneration. I'm not going to draw the diagram. Remember, diagram draw nahi karunga main. That definitely I'll tell you directly its effects. So what are its effects, my dear? You know that its effect was, that is we are getting, my dear, in this W net remains same, QS has been reduced as it is regeneration. So we are getting heat from exhaust. So definitely it will get, QR will be get decreased, and my dear, the mean temperature of heat addition has been increased. Mean temperature of heat rejection has been decreased. Now, my dear, can you tell me what about the efficiency? Efficiency is function of MA into MR. Sorry, 1 minus MR by MA. So definitely it will going to be increased. So this thing we have seen in the regeneration, right? When, my dear, when I talk about ideal regeneration, in that we find out efficiency of ideal regenerative Breton cycle. That is, my dear, what we have find out? Well, we have find out 1 minus T1 by T3 bracket what RP, that is pressure ratio, raised to power gamma minus 1 upon gamma. This thing we have find out, right? Yes or no, my dear? Okay. And after this, my dear, after this we have drawn the curve that is like this for efficiency of simple as well as for ideal. So it is what, my dear? It is efficiency, it is pressure ratio, right? And we have drawn, it is nothing but what? Simple, right? And same thing, my dear, we are getting like this. And it is what, my dear? It is ideal. It is ideal regenerative Breton cycle. It is what, my dear? Simple cycle. Simple Breton. Okay, I hope you got it. Yes or no, my dear? Here we go. Here we go. See, the opposite relationship is there. Okay. So here we'll go for next slide, and that is, my dear, then we have seen intercooling for intercooling na in a gas turbine. That is what, my dear? Intercooling. What we have seen? Intercooling. Right. In that, what we have seen, my dear, what are the effects? So we have seen the work of compressor has been dropped. That means W net, WT there is remains constant. So what will be the W net, my dear? W net has been increased. That means heat supplied is what, my dear? It has been increased now. Intercooling, we are going to cool, then we have to supply the heat, right? QR is also increased, my dear. Then TMA, mean temperature of heat addition, it may increase or it may decrease. Okay, but TMR is going to be decreased, my dear, for sure, right? And, my dear, what will happen to efficiency? Because there is a drop in pressure as in the intercooling. So it will be what, my dear? It will be what? Drop. It will be drop. Okay. Here you have to make a note that regeneration is very effective when it is combined with what? Intercooling, and the efficiency is improved by almost 15 to 20%. Right? Yes or no? Then, my dear, we have seen reheating. And supposed to be, if I have to do what is condition for perfect intercooling. Perfect intercooling के लिए condition क्या है बच्चा? In perfect intercooling, we have seen intermediate pressure is equal to, my dear, what? P3 into P1. What? P2 into P1, right? And we have also seen that temperature, perfect intercooling means what, my dear? Temperature will be equal. That is what? T3 is equal to T1. Right now, that means temperature after intercooling is equal to the initial temperature in the cycle. Okay? And after this, my dear, we have gone for reheating. Reheating in a cycle. Reheating, we are just discussing this thing for gas turbine. Gas turbine. Okay, I repeat. Here, that is what, my dear? Reheating. So reheating के लिए जब हम गए, so what we have seen, my dear? That is WC. What happened to WC? WC is remain same. I am not going to draw the diagram because diagram draw करूँगा and it will need more time. Okay, and WT is what, my dear? Reheating है. So definitely the number of stages of expansion will be increased. So definitely WT is going to increase. What about W net? It is also increased. What about QS? Reheating is there, so it is increased. What about QR? It is also increased. What about the TMR, mean temperature of heat addition, rejection? It is what, my dear? It is increased too much. What about the mean temperature of heat addition? It has increased, right? My dear, can you tell me what about efficiency? So reheating is there, so there is a drop in pressure. So I can say, my dear, it is dropped. That is, efficiency has been decreased. Remember one thing, okay? Now, my dear, I'll go for next, right? Now, this thing we have seen for gas turbine. After this, we are going to discuss about compressor. What, my dear? Compressor. So we have seen compressor in that. And my dear, we have seen dynamic compressor, we have seen reciprocating compressor, and then we have done the classification as well, right? On the basis of classification, right? But we are going to directly, my dear, for reciprocating compressor, and we are going to see the work done. Work done required for reciprocating compressor without clearance, with clearance. So first of all, I'm going to write it for without clearance. So my dear, it is none other than what? N upon N minus 1 P1 V1 into, in bracket, what, my dear? P2 by P1. I'm just revising your formulas, right? N minus 1 upon N minus 1, right? Then, my dear, if you want to calculate power, then it should be what? W per cycle. It is what? It is per cycle. Work done, work input per cycle. Work input per cycle multiplied by N upon 60. That will be in kilowatt, okay? This thing we have seen. After this, my dear, we have also gone for, it is just for, it is without clearance. Here I have not considered any kind of clearance. But my dear, if I go for W per work input required per cycle with clearance, then it should be what, my dear? It should be what? कितना आया था बच्चा ये हमारा? ये आया था, that is what, my dear? N upon N minus 1 P1 V1 minus V4, and V1 minus V4 is nothing but an actual quantity which is entering inside the compressor, and it is P2 by P1 minus 1 upon 1, and it is for what, my dear? It is for with clearance. So we have observed, or we have calculated one thing over here, that if the actual volume entering inside the compressor in both the cases, if it is same, that means V1 is equal to V1 minus V4. V1 is what, my dear? Actual volume entering inside the compressor, and here it is what? V1 minus V4, that is VA. Supposed to be this VA and this VA are equal. Then we can say the work required for compressor with clearance and without clearance will be same. Okay? Will be same. I hope you got it. Here we go for next. And after that, my dear, we have gone for volumetric efficiency. क्या देखा था हमने? We have gone for volumetric efficiency. And in that, my dear, eta vol, we have derived what? VA by VS. And that we have derived, my dear. क्या लेकर आए थे हम इसको? It is none other than 1 minus C in bracket. What, my dear? P2 by P1 raised to power 1 by N minus 1. Some people, कुछ लोग इसको अलग तरीके से भी लिखते हैं, 1 plus C minus C P2. इसको कुछ लोग ऐसे भी लिख सकते हैं, plus C minus C P2 by P1 raised to power 1 by N only. It is also right. Okay. And what is the condition so that eta vol becomes 0? This 0 कब होगी? It is 0 when, my dear, pressure ratio P2 by P1 is equal to 1 upon C plus 1 raised to power N हो जाए. Then and only we found this is equal to 0. Okay. I hope you got it. And we have, okay. And after this, my dear, we have gone for multi-staging. And in multi-staging, we have seen, in multi-staging, why we are going for multi-staging? To save the work and to increase the volumetric efficiency. If you are compressing at in a single stage, my dear, for a high pressure requirement, then definitely work required will be high and volumetric efficiency is going to be dropped. Okay, क्या हो जाएगी वो drop हो जाएगी. Okay, so my dear, this is the problem. And one more thing that I want to tell you, that supposed to be, I have 3 stage, 4 stage, 5 stage, or we can say n number of stages are there. Supposed to be, here I draw. Supposed to be this PV. Okay, here I draw. It is what? 3 stage, right? 1, 2, 3, 4, 5, 6. Right? So overall pressure ratio will be what, my dear? P6 by P1. It is none other than what? P2 by P1, right? Multiplied by what? P4 by P3. Are हाँ या ना बच्चा? Yes or no? Please tell me. Yes. P4 by P3 multiplied by P6 by P5. Right? Yes or no? Yes or no? But my dear, supposed to be I put one condition, that is pressure ratio produced in each stage is same, supposed to be for each stage, right? Then I can write overall pressure ratio is equal to, my dear, pressure ratio of any stage. We can say P2 by P1 raised to power n, and n will be what, my dear? N will be number of stages. And what should be the work required? Work required will be what, my dear? That is n into work required in 1, 2 stage, or 2, 3, 3, 4, right? I hope you got it. Agar pressure ratio same hai to, then and only we are going to apply this condition. Okay, so this is all about what? The compressors. And after this, my dear, we have gone for, uske baad what we have seen? We have seen free air delivery, FAD. And in the FAD, my dear, what we have come with? We come with the one formula, and that is none other than what, my dear? P1 V1 minus V4 divided by what? T1 is equal to P2 V2 minus V3 divided by what, my dear? T2 is equal to, that is what? Total pressure, total volume divided by total temperature, right? And it is none other than, ये किसके लिए था? FAD, that is free air delivery के लिए था. I hope you got it. Okay. Then, my dear, we have derived for what? Cylinder dimensions के लिए we have required, that is multi-staging में. In multi-staging, we required cylinder dimension as well, right? So for that, my dear, what we have seen? What we have seen is, for that we have seen the equation, and that is what, my dear? P1 D1 square is equal to P2 D2 square is equal to P3 D3 square. And it is when L1 is equal to L2 is equal to 3. That is, length of stroke will be equal. Okay, ये चीज हमने देखी थी. And after this, my dear, we have gone for dynamic compressor, right? इसके बाद हमने dynamic compressor देखा था. That is centrifugal compressor. Yes. हाँ जी बच्चा, इसके बाद सेंट्रीफ्यूगल कंप्रेसर देखा था हमने. दैट इज व्हाट, माय डियर? सेंट्रीफ्यूगल कंप्रेसर. We have seen, my dear, centrifugal compressor, right? And in that we have seen, my dear, what? Entry is axial but flow is radial. Entry क्या होती है? Axial होती है, but flow क्या होता है बच्चा? Radial होता है. क्या होता है? Radial. But before that what we are going to see, हम इसका सबसे पहले देखेंगे the velocity triangle. Velocity triangle we are going to see. ठीक है, velocity triangle देख लेंगे. But before that, I want to tell you that I'm going to tell you about what power required for it. So power required का formula क्या देखा था बच्चा? यहाँ पे हमने VW2 U2 minus VW1 U1. टर्बाइन में अपोजिट हो जाता है, टर्बाइन में अपोजिट होता है, राइट? And it will we have find out what? V2 square minus V1 square by 2 plus what? Centrifugal effect, that is U2 square minus U1 square by 2 plus relative velocity, right? Or we can say reaction effect, and that is, my dear, VR1 square minus VR2 square by 2, right? This thing we have seen, right? And then, my dear, उसके बाद we have seen what? The pressure variation, because that centrifugal compressor have 3 parts: casing, impeller and diffuser, right? So in that we have seen pressure and velocity changes, or we can say variation. So कैसे हुआ था? That I'm going to draw, my dear. So first of all, it is what? Casing, then we have impeller, and then we have diffuser, right? So here I draw. So, my dear, first of all, when it enter in the casing, the pressure has been dropped. Then, my dear, when it go for impeller, it is going to increase. And, my dear, in diffuser, it also increased in a high limit, right? So it is what? It is diffuser, it is impeller, and it is what? It is none other than casing. It is impeller. It is diffuser. DIFF. I have written in short. And it is variation of pressure. Okay, my dear. Then we have seen that is when the pressure has been dropped, there is increase in what, my dear? Velocity, like this. When there is what? Increase in what? Pressure in impeller. It is just because of what, my dear? It is just because of we have static pressure rise हो रहा है, due to which the pressure has been increased. But in impeller, what will happen, my dear? Kinetic energy is going to increase. So definitely the velocity is going to increase. Right? And after this, my dear, wait. Then we have, there is a drop in velocity in diffuser. In diffuser, pressure is increases at the cost of velocity. So this is what, my dear? Velocity. Change of velocity in the centrifugal compressor. This kind of variation we have seen. Right? So no, bacha. And after this, we have seen the velocity triangle for it. Velocity triangle kaisa tha? Let me draw. Supposed to be, this is the blade. So why it is axial entry? It have the axial entry. So see, it have the axial entry, right? And it will enter. This will be what, my dear? Velocity. That is relative velocity. It should be absolute velocity, right? And this absolute velocity, right now, V1, and this will be equal to, okay, what it should be? It should be U1. ये क्या होगा? U1. ये 90 degree, and this will be what, my dear? This is none other than this will be none other than what, my dear? Okay, wait. This will be क्या होगा बच्चा? ये हमारा हो जाएगा ब्लेड एंगल. सॉरी, ब्लेड एंगल तो ओह सॉरी. इसको थोड़ा सा लाइक दिस. हाँ, ऐसा कर लो, इस सेट कर लो, ज्यादा बेटर है. इट विल बी लाइक दिस. तो ये 90 डिग्री. It is what? It is your VR1, which is VR1, right? So it should be theta, blade angle. ये हो जाएगा absolute velocity angle. It is equal to V1 is equal to VF1, axial entry, and it should be what? Blade velocity U1, right? VW1 is 0, right? When it is the axial entry, okay. It will come outside with the velocity of what? Relative velocity. It will come outside with the help what? With relative velocity like this. And in this direction, my dear, in opposite direction, we have V2 absolute velocity, right? And when we join these two things, what do you get, my dear? जब इन दोनों को join करते हैं, what do you get? I'll tell you. And इन दोनों को बीच से, that is what? It is our axial component. That is, sorry, thrust. It is axial thrust, and it should be what, my dear? VF2, flow velocity. It is absolute velocity, and it should be what? Relative velocity, जिसके साथ ये बाहर निकलता है. And angle क्या होगा बच्चा यहाँ पे? Phi. यहाँ पे क्या होगा? That is beta. That is beta. And now you have to tell me it should be what? It is none other than your VW2. And ये क्या होगा पूरा यहाँ से यहाँ तक? It should be your U2. It is none other than, my dear, U2. Right? So this is the velocity triangle for what? Centrifugal compressor. Okay. Now, my dear, good afternoon. Good afternoon. Now, my dear, this is what? This is for centrifugal compressor. The velocity triangle for centrifugal compressor we have seen. My dear, after this, we have seen that. See, the inlet velocity triangle will remain same. This is what? This is inlet velocity. This is inlet velocity triangle, right? Now, my dear, after this, we have seen what? Blades. And we have seen radial blade. Right? We have seen the radial blades. And we have, when there is a radial blade, my dear, जब radial blade होता है, so velocity triangle कैसा होता है? ऐसा. जो exit का, I'm talking about exit. Exit का कैसा होता है बच्चा? ऐसा कुछ. Right? And it is none other than ये जो चीज होती है, it is equal to what? ये किसके बराबर होती है? U2 is equal to VW2 के बराबर होती है. Right? And it is your phi. ये क्या होगी बच्चा? It is your velocity, that is relative velocity, and it will be equal to what? Flow velocity. Flow velocity and relative velocity are equal in case of radial blades, right? And it is what? Absolute V2 at angle of beta, right now. And when we are talk about, my dear, what? Forward curve blade. Forward curve blade, how it should be? I'll draw it again. See. Right? Yes or no? It is none other than what, my dear? Wait. Okay, it is बच्चा what? Beta. It is phi. Right? ये क्या था बच्चा हमारा? VR2. It is what much, my dear? It is none other than V2, and it is what? VF2. Right? ये क्या था हमारा? It is what? It is my U2 narrow, and it is what? UW2. It is what? VW2. That is wall component, or you can say tangential component, right? And what about the backward? Backward. So here I draw for backward as well. See, my dear. Backward के लिए draw कर रहा है. It is none other than absolute velocity triangle. Sorry, absolute velocity, and it is, my dear, relative velocity through which the air will come out or leave the blades of what, my dear? Blades of what? Impeller. It is V2. ये क्या होता था बच्चा? बीटा. ये क्या होता था हमारा? phi. Right? It is 90. It is what? VF2. Right? Now you have to tell me. It should be what, my dear? VF2, V2. It is what, my dear? It is none other than tangential component of velocity, that is wall component, VW2. And my dear, this will be what? This will be none other than your U2. Okay? So this is what? This is for backward curve rate. ऐसा था, right, my dear? And I want to tell you that it have what? It is the high efficiency and what? Wide operating range. It have wide operating range as well. It have efficiency will be what, my dear? Its efficiency is what? Low, and it's have narrow operating range. And it is, this radial one is, it is in between these two. इन दोनों के बीच में होता है. Okay? So here we go for next. My dear, slip. Slip, what is slip? You know that. Slip is what? When we assume, I'll explain, okay? Slip is what? Slip is nothing but in ideal condition, we assume that the impeller have infinite number of blades, right? But when we go in actual condition, we have limited number of blades. So what happened? The air is trapped between the blades and passage between the blades. Then what happened? Due to the inertia effect, there is a pressure difference created, right? And due to this pressure difference creation, what happened? The air which flow along what, or which flow over the surface of what? Blade profile, they start leaving it. उससे deviate होते हैं वो. They start deviating it from it, and it is known as what, my dear? It is known as slip. This is known as slip. Okay? इसको क्या बोलते हैं? Slip बोला जाता है. And my dear, it is slip. And then, my dear, we have seen slip factor as well. What? Slip factor. And slip factor is nothing but what, my dear? Theoretical power upon ideal. Theoretical power upon ideal power. And it is none other than, my dear, denoted by phi s. It is given by VW2 minus ideal power in, power in ideal condition, that is VW2 dash, right? I hope you're getting, okay. This is a revision session. I can tell you, you have to attend the classes for it. You can join me in the Testbook Select, or you can join me, or you can just see or take the reference of the lecture which is available in the Testbook Gate itself. Okay, I hope you got it, my dear. After this, what we get, that is phi s. That is what, my dear? VW2 actual condition. That is in ideal condition. We have velocity U2, right? So this will be the slip factor. After this, my dear, we have power input factor as well. What, my dear? Power input factor. So power input factor is nothing but what? It is a ratio of actual power to the theoretical power. That is ideal. And it is none other than, my dear, actual power will be what? Actual power is, we got, my dear, F mass flow rate into M into slip factor into is equal to U2 square, right? We got this one. And remember one, the value of this one is from 1.035 to 1.05. Okay, I hope you got it. After this, my dear, after this we have seen pre-whirl component. Why we give the pre-whirl component? What is pre-whirl component? Pre-whirl component in what, my dear? In compressor. Why we are providing pre-whirl component? What happened? The compressor which are run at very high speed, what will happen? There is a chance of generation of a shock wave at starting. So we provide some kind of pre-rotation so that the relative velocity will going to decrease by keeping that is what, my dear, impeller velocity, or we can say the blade velocity same. उसको सेम रखकर, उसको कांस्टेंट रखकर इसको डिक्रीज करते हैं. उससे क्या होता है? वेलोसिटी विल डिक्रीज, डेफिनेटली द चांसेस ऑफ जनरेशन ऑफ शॉक वेव will be reduced. Okay, my dear, after this we have seen surging, right? And what is surging? Surging is there, then we have choking is there, right? And it happens when closing of wall. When there is a closing of wall, at that time it happens, right? And what is it? What did it mean by, right? Please tell me. Haji bacha, what happens in this? What happened? Mass flow rate become what? Become lesser than the corresponding maximum pressure. Corresponding to maximum pressure के corresponding इसको जितना होना चाहिए उतना ये होता नहीं है. Okay, so that's why we called what? Surging. It is called as what, my dear? Surging. And remember one thing, there is choking also. Choking is what? Choking is nothing but a maximum mass flow rate. Maximum mass flow rate. Okay, and it happens when, कब होती है ये? Generally when Mach number corresponding to what? Corresponding to the relative velocity. When that is Mach number corresponding to relative velocity become what, my dear? Sonic. Okay, जब relative velocity होगी blades की, when relative velocity becomes sonic, my dear, come in the range of sonic, so the mass flow rate become higher irrespective of pressure. Okay, my dear, so remember one thing. And another thing is there, another thing, that is stalling. So due to improper design of blade, what happened? Due to the improper design of blade, what happened? That the air, that is a particle of air, that is air particles, or we can say the fluid particles, starts leaving or deviates from the blade profile. Blade profile से जो है deviate हो जाते हैं automatically. So it is known as what, my dear? It is none other than stalling. You remember one thing, what is, some people have the doubt that then what is difference between surging and stalling? So I want to tell you, surging is a periodical formula. It's going to be occur, no issue. But my dear, stalling you can avoid. Stalling you can avoid by a proper design of blades. Okay. Okay, here we go for next. Stalling we can avoid by what? Proper design of blades, my dear. Okay, after that, my dear, we come to axial compressor. क्या देखा था हमने उसके बाद? Axial compressor. We have seen axial compressor. What, my dear? Axial compressor. And in that what we have seen? We have seen, my dear, I'll write the formula directly, okay? Important formula so that you have an idea. In that we have seen, first of all, that is degree of reaction. Velocity triangle will remain same maximally. I will draw the velocity triangle, don't worry. And we have seen first formula, important formula, that is what, my dear? Degree of reaction. That is enthalpy drop along the moving blade is nothing but enthalpy drop in the moving blade plus enthalpy drop in what, my dear? In fixed blade. Right? Yes or no? Yes or no? My dear, then we have seen for centrifugal compressor. Centrifugal compressor, that is, my dear, degree of reaction for centrifugal compressor, what it should be? It is none other than for what? So, my dear, in centrifugal compressor, we have U2 square minus U1 square plus VR1 square minus VR2 square, right? Divided by what? 2 into VW2, what? U2 minus VW1 U1, right? And this will be what? Degree of reaction for centrifugal compressor. Okay, my dear, after this there is a degree of reaction for axial compressor as well, and we have derived the equation for it, and that is what, my dear? Vf upon twice U upon tan of beta 1 or tan of theta plus tan of pi, you can say. Beta 1 or beta 2. Some people took what? That is blade angle at inlet is what? Beta 1, and blade angle at outlet beta 2. Some people took that is what? Theta and phi, as I have taken in this class. Okay, my dear. So here after this is what? This is degree of reaction for, and what is the condition required for 50% degree of reaction? That 50% degree of reaction means, my dear, the contribution by the moving blades will be 50%. And the condition is what, my dear, for it? That is what? V1 is equal to VR2, V2 is equal to VR1, alpha 1 is equal to what, my dear? Alpha 1 is equal to what? It is none other than beta alpha is equal to pi, and alpha 2 is equal to theta. Okay, these are the conditions required for 50% degree of reaction. After this, my dear, we have seen what? We have seen and after this we have seen polytropic efficiency or small stage efficiency. We have seen polytropic efficiency. I will not cover the theory part, okay? डिटेल में थ्योरी में देखेंगे, जहां रिक्वायर्ड है वहां पे मैं डिस्कस करूंगा, डोंट वरी. पॉलीट्रॉप, दैट इज वी हैव सीन पॉलीट्रॉपिक एफिशिएंसी, एंड इट इज व्हाट, माय डियर? eta pc will be what we have seen, that is none other than what, my dear? Gamma minus 1 upon gamma into n upon n minus 1, right? Yes or no? It have also formula, that is what ln of, that is stagnation temperature, divided by T naught 1, right? Divided by ln of T naught 2 divided by T naught 1. Okay, this is required formula for polytropic efficiency. I hope you got it here. Yes or no, my dear? Now I'll go for next. See, after this, my dear, after this we have gone for what? Vapor power cycle. That is what we have discussed, Rankine cycle. And it is very important. It is very important. यहाँ पे ध्यान रखना बच्चा. It is very important section. So listen me very carefully. First of all, let me draw its diagram. मैं diagram draw कर देता हूँ इसका. Okay. Okay, so it should be what, my dear? Let me. Okay, and it is like this. Right? Yes or no? It is 1, 2, it is, my dear, 3, it is 4, right? Here we are supplying heat, right? From here we are getting work done, turbine. Here we are rejecting heat, and we are supplying what? Work input to the pump. It is what? TS diagram. Okay, here we go. Here we go, my dear. चलें आगे. So you know that this is what? Isentropic what? It is nothing but a isentropic compression, you can say, but it is nothing but VR liquid from condenser to the boiler pressure. Bring कर रहे हैं उसको. This compression from liquid, that is condenser. It is what? Condenser. It is what? Boiler pressure. That you know, right? 2, 3 is what, my dear? 2, 3 is nothing but what? A constant pressure, heat addition. 3, 4 is nothing but isentropic expansion, and 4, you know that. This thing you know that, right? My dear, here we go. What about the W net? W net will be what, my dear? WT minus WP. So what is WT? You know that it should be what? It should be none other than S3 minus H4, and WP is what, my dear? It's open system. It's an open system, so I can say it should be S2 minus H1. It is also equal to what? It is also equal to VFDP. VFDP. And VF what? VF of 1. 1 ka lenge. DP is what? P2 minus P1. Okay, it is also equal to this one. Right? And my dear, after this, we have seen specific steam consumption, and that is none other than mass of steam divided by consumed to the power, and it is what? It is in kg per second, and here it is in what? Kilowatt. Okay, so you will get, and after this, my dear, we have also seen another formula, that is none other than 3600 divided by W net, and it is none other than, my dear, it is in kg per kilowatt hour. It is in kg per kilowatt hour. It's unit, right? This is what? Specific steam consumption, right? And after this, my dear, heat rate, that is HR. It should be none other than what? Heat rate, what we have seen, heat rate will be, my dear, it is none other than, that is heat supplied divided by the W net is equal to 1 upon efficiency. Yes or no? It is none other than 1 upon efficiency. Yes or no, my dear friend? Of course it is, right? And you should know that eta of Carnot is greater than from eta of Rankine, right? But again, I want to tell you that is work done produced in Rankine is quite higher than work done produced in Carnot. But still, you have questioned that, but still, why then efficiency is quite less? It is all about what? Mean temperature of heat addition and mean temperature of heat rejection, right? And after this, my dear, after this, we have seen, that is, we have decreased, if I decrease the condenser pressure, we have seen the effect of variation of parameters. So first of all, I'm going to decrease condenser pressure. Then what I'll see, what will be the effect on this cycle after dropping the condenser pressure. My dear, we have WP, pump work will be going to increase. Then my dear, WT is going to increase too much. Then we have W net also increase, right? What about efficiency? Efficiency is going to increase, right? Dryness fraction is going to drop. If dryness fraction is going to drop, my dear, then what will happen? That is, chances of blade erosion is quite high, right? Yes or no? What about the mean temperature of heat addition? It is going to drop. And again, I'll tell you, mean temperature of heat rejection, it is rapidly drop, right? And we have, that is, heat supplied will going to increase. What about the heat rejection? Heat rejection, again, it is going to increase, right? Okay, I hope you got it. Or we cannot say, zaruri nahi increase hoga, but it is mostly increase, right? Or we cannot say, okay? Yes, it's an imaginary cycle. It's an imaginary cycle. I repeat, it's an imaginary cycle. Okay, so this is all about what? Effect of, then my dear, if I increase the boiler pressure, then what will be the effect? That is WPC. This thing we can see in a class in a very good manner, right? Yahan pe that I'm discussing directly factors, right? And here WT has been increased, and how it has been increased. If you want to know इधर ये increase कैसे होता है, decrease कैसे होता है, आप ये कैसे बोल रहे हो, my dear, you have to follow the classes of mine. जो अवेलेबल है लेक्चर्स उसको फॉलो करो. डेफिनेटली उसमें मैंने बहुत अच्छे से एक घंटे में बताया कि ये कैसे इंक्रीज होता है, कैसे डिक्रीज होता है. ओके, बट W net as it is revision class, so we are going to discuss up to point only, right? QS क्या होता है बच्चा? Heat supplied. Heat supplied क्या हो जाता है? That is reduced, right? Heat, that is mean temperature of heat addition, it is going to increase, right? TMR पे there is no effect. TMR remains constant. Then my dear, what efficiency is going to increase? What about most important is that dryness fraction. So my dear, dryness fraction drops. Dryness fraction drops means what? The chances of erosion of blades is quite high. Okay. After this, my dear, after this we have done what? Superheating. What we have seen? Superheating. And in the superheating, my dear, what happened? WP remains same. And then WT, it's quite what, my dear? WT quite increased. Then agar WT increase हो रहा, definitely W net will going to increase, right? Theta QS is going to increase. What about QR? QR also increases. Heat rejection ये भी increase होता है, right? QR क्या होता है बच्चा? Increase होता है. Dryness factor, sorry, उसका mean temperature of heat addition, it is also increase, right? Mean temperature of heat rejection is quite constant. Then my dear, we have what? Dryness fraction. Dryness fraction क्या होगा बच्चा? It may drop or it may increase. It depends. It depends. So यहाँ पे chances erosion के बढ़ते भी हैं और घटते भी हैं. Okay. And remember one thing, that what will happen to efficiency? It is going to increase. So this is all about superheating, PB, PC, and PD, right? Till now, I know that थोड़ा सा फास्ट हुआ है. You have lot of questions कि सर ये सब चीजें आपने लिख दी हैं. So this is class just for revision. I'm going to just note down, or we can write the important points or important formula which is important as per the examination, right? Still it has not been over. बहुत कुछ बचा हुआ है अभी. But right now my throat is quite paining now, right? तो ज्यादा ही पेन हो रहा है. So guys, what we do, we're going to continue in the next class, or but in the next class I'm bringing what, my dear? I'm bringing lot of what question, that is model question paper. So next इसमें हम model question paper ही करेंगे, and we'll try कि उसमें ही revise कर ले concept को, because it is like one way हो रहा है, because इसलिए attendance भी कम आ रही है बच्चों की, ठीक है ना? So उसी में revise हो जाए, that will try in that fashion only. Okay? So guys, कल देखते हैं, फिर कल मिलते हैं. Okay? Yes, anybody have any questions? Please let me know then. कोई क्वेश्चन होंगे तो बताओ आप. Yes, please tell me. If you have anybody questions, please let me know. No questions? So, okay. We'll see you in the next class. So take care. Bye-bye. Shabba khair. And thank you so much for your presence. I will see you in the next class. Okay. MCQ में चलते हैं. Okay. Next, Rahul definitely will go in the MCQ only. Okay. So I have taken, see, in the Rankine, we have regeneration, we have reheating are left. Otherwise, I have completed steam turbine is left. So I will try कि उसको जो है उसी में revise करा दिया जाए. And remember one thing also कि that I will also cover the renewable energy part as well. Okay. Renewable energy पे भी question लेकर आते हैं आप. Okay. So guys, take care. Bye bye. Shabba khair. And one more thing that I want to tell you, that please take care of yourself. And जाने से पहले do hit like, share, and subscribe the channel. Okay. Okay. So guys, we'll see you in the next class. So thank you so much. Bye bye. Take care. And God bless you. And most important thing, that please stay at home, stay safe, stay online with the testbook.com.